In the last lesson, we examined the table method, which can be used to organize results when testing the sufficiency of a statement. Now, during that lesson, we solved the following question. Here we saw that when x equals 1, the answer to the target question is yes, and when x equals 4, the answer to the target question is no. Since we were unable to definitively answer the target question, we correctly concluded that statement 1 is not sufficient. Now, in that lesson, we saw that the table method can be useful for demonstrating that a statement is not sufficient. However, if the statement you are examining is sufficient, as is the case with this example, the table method will be inconclusive. For example, the table results here suggest that if x is positive, then 6x will always be less than 7x. But it may very well be the case that we have simply chosen bad numbers to work with. Now, in this example, the table results suggest that if x is odd, then x will always be prime. However, in this example, I have done a poor job selecting possible values for x. Now, if I had chosen 15 as a possible value for x, then the answer to the target question would have been no, 15 is not prime, in which case we would be able to conclude with absolute certainty that statement 1 is not sufficient. So as you have seen, the table method is useful when we suspect that a statement may be insufficient. More importantly, the table method will only yield conclusive results if we are able to choose numbers that yield different answers to the target question. So when you are choosing numbers for your table, your goal should be to choose numbers that will cause conflicting answers to the target question. To accomplish this, we want to choose good numbers. So what are good numbers? Good numbers are numbers that represent a nice cross-section of all numbers. Some good numbers include -10, -1, -1/2, 0, 1/2, 1, and 10. Here we have negative numbers and positive numbers. We have 0, which is a special number that has some properties that other numbers don't have. And also 0 is typically an easy number to plug into equations. -1 and 1 are also typically easy to plug into equations. Finally, two numbers that often prove to be very useful are -1/2 and 1/2. These numbers have some very interesting properties that differ from properties of other numbers, so keep them in mind. Now, these aren't the only numbers you should consider choosing when using the table method, but they are a good start. Now, here's a question we looked at in the last lesson. This question illustrates the utility of -1/2 and 1/2. Now, in most cases, when we take a positive number and square it, the squared number is larger than the original number. 2 when squared becomes 4. 5 when squared becomes 25. 10 becomes 100, and so on. However, numbers between 0 and 1, such as 1/2, become smaller when squared. This concept is tested often on the GMAT, so watch out for it. So when x equals 2, the answer to our target question is yes, and when x equals 1/2, the answer to our target question is no. In this case, we can say with certainty that statement 1 is not sufficient. Here's another question. We want to determine whether x plus 1 over x minus 1 is less than 0. Statement 1 tells us that x is less than 0. Is this statement sufficient? Well, if you're not sure where to begin, why not try the table method and see what information you can collect? So we'll choose values for x such that x is less than 0. Then using these values, we'll ask our target question, is x plus 1 over x minus 1 less than 0? Okay, what's a nice number to start with here? Keep in mind that x must be less than 0, so we cannot plug in numbers like 0, 1, and 10. Well, how about -1? If x equals -1, then our expression evaluates to be 0. So when x equals -1, the answer to our target question is no. X plus 1 over x minus 1 is not less than 0. Now, what's another nice number we can choose here? Remember, our goal is to choose numbers that cause conflicting answers to the target question. So we want to choose a number such that the answer to our target question will be yes. Now, we've already tried -1 as a value for x, so now we might try x equals -10 or x equals -1/2. Let's try x equals negative 1/2, which we'll replace with negative 0.5 for faster calculations. Now, if x equals negative 0.5, then we can evaluate our expression by replacing x with negative 0.5. When we do this, we get 0.5 over negative 1.5. At this point, we don't really need to continue evaluating this. We have a positive number divided by a negative number, which means the quotient will be a negative number. That's all we really need. So when x equals negative 0.5, the answer to our target question is yes. X plus 1 over x minus 1 is less than 0. Since we have two conflicting answers to our target question, we can be certain that statement 1 is not sufficient. Okay, let's look at two more examples. In this question, we are told that k is a positive integer, and we want to determine whether k plus 5 over k is an integer. While we could spend some time rephrasing the target question, I want to jump straight into examining the statement because this is an area where students often experience difficulties. The statement says that when k is divided by 5, the remainder is 1. So what are some possible values for k? Well, k could equal 6, since 6 divided by 5 is 1, with a remainder of 1. Now, if k equals 6, then k plus 5 over k simplifies to be 11 over 6. So when k equals 6, the answer to our target question is no. K plus 5 over k is not an integer. Now, what other values can we choose here? Keep in mind that we want to choose a number that causes conflicting answers to the target question. So we want to choose a number such that the answer to our target question will be yes, k plus 5 over k is an integer. Well, another possible value for k is 11. If k equals 11, then k plus 5 over k simplifies to be 16 over 11, which is not an integer. So when k equals 11, the answer to our target question is still no. If we choose 16 as a possible value for k, then the answer to the target question is still no. And if we choose 21, the answer to the target question is no. So can we conclude that statement 1 is sufficient? It certainly looks that way. Unfortunately, we are forgetting an important value for k. If k divided by 5 gives us a remainder of 1, then k could also equal 1, since 1 divided by 5 is equal to 0 with a remainder of 1. Now if k equals 1, then k plus 5 over k simplifies to be 6, and 6 is an integer. So when k equals 1, the answer to our target question is yes. So now that we have two conflicting answers to the target question, we can be certain that statement 1 is insufficient. Here's one last example. Here we want to determine whether k plus 1 over 2 is an integer. Now statement 1 tells us that k is a prime number. On the GMAT, when you are told that a number is prime, you are often being tested on your knowledge on one of two important facts. The first fact is that prime numbers have exactly two positive divisors, and the second fact is that all prime numbers are odd except for the number 2. Now the second fact is being tested here. So let's use a table and begin by choosing 2 as a possible value for k. If k equals 2, then the expression simplifies to be 3/2. So when k equals 2, the answer to our target question is no. K plus 1 over 2 is not an integer. Now let's choose 3 as a possible value for k. If k equals 3, then the expression simplifies to be 2. So when k equals 3, the answer to our target question is yes. K plus 1 over 2 is an integer. So we can now say with certainty that statement 1 is not sufficient. So, to summarize, the table method can be useful if you suspect that a statement may be insufficient. If you aren't sure how to solve a data sufficiency question, the table method may help provide some insight into whether or not a statement is sufficient. When using the table method, your goal is to choose values that cause conflicting answers to the target question. When looking for good numbers to use in your table, consider these ones, And finally, be sure to adhere to any restrictions regarding the numbers you are allowed to use.